Assalamu alaikum, everyone. I am Safraz and I am presenting SwiftBot. On behalf of me and my team, I'd like to thank the Kaavish committee and our advisors for their constant and ever ready support. The key motivating factor came from the observation of the problem of untimely and unsecured deliveries within large office spaces and university campuses. We wanted to solve that through an indigenously developed prototype delivery service robot. Also, in recent times, minimizing human-to-human contact and facilitating the frontline health workers with safe and hygienic delivery of medical supplies to aid them also became a good motivator. Studying other people's work is learning also an integral part. So the sources that significantly helped us in our projects are mentioned but not limited to service robots for hospitals, sensor and sensory fusion in autonomous vehicles, and evaluation of 2D SLAM techniques available in robot operating system, and more. The other research we completed were to look at commercially available products of similar capacity. Among them were prominent Starship technology robots, Domino DRU robots, Carry robot, Tele-Retail robot, and Marble robot. As Swift as SwiftBot is a complete product, it has an end-to-end user journey starting from the customer-facing app where the user comes in, signs up, and books or sends a parcel, which is all stored and logged in our cloud storage and processed through our central server and then sent to the hardware at the robot. The robot then completes a journey from point A to B, and then the security feature, either the secure unlock face ID or the security pin, makes sure that the delivery is secure so that the user can be at ease.
Okay, so let's talk about the solution design. This figure, it briefly talks about the different modules that are there in our system. So we have the Android app, we have the central server, we have the Python server, we have the admin portal, and then we have the robot, which is further divided into different modules such as the obstacle detector, then we have the driving module and SLAM, which is responsible for creating the mapping and assisting the obstacle detection and driving module. We will further look into the working of the system in the upcoming slide. Okay, so this figure talks about the UML of our system. So we have the robot, the user, the lock, the facial recognition, the booking, and the central server. So let's quickly talk about the functions here. So we have the get location functions, which gets the current location of the robot, which can be used to calculate the remaining time of the booking. Then we have the get next journey, which the robot basically calls the function in the central server for to get the next booking. Then we have the mark current booking as finished, and also the function to get the current booking status and all the current booking details. Then we have the user. For the user, we have user login, user sign in to get all the bookings of the user. For the lock, we have the open lock, which gets called when the app wants to open the lock for a booking, or when the facial recognition wants to open the lock. And then we have the get lock status. For the facial recognition, we have mainly two functions. The first one is training on a video, and then we have the second function is to basically validate a face against the trained data. For the booking, we have the get all the live bookings, get the bookings of a user, get the current booking, and get the next booking. For the central server, which are basically the functions that get called in the different modules of our system, we have the get booking, we have the get all the locations, get all users, and open lock. Now let's talk about the ERD of our system. So as you can see here, our ERD looks very simplified. The reason behind that is we don't have much data in our system. So as you can see here, the main data that we have in our system is the booking, the map points, and the user. Okay, so this is a simplified, this is a flow chart of the working of our system. So that the way in which our system works is it gets the booking from the queue from the central server, then it reaches the sender and opens the lock automatically so that the sender can place the parcel in the container. Once that is done, the robot starts its journey towards the receiver. Once it reaches the receiver, it checks whether the password has already been added so that it can automatically open the lock. If this hasn't been done, it goes to the next procedure, which is to open the camera so that it can validate the face of the receiver. If the face is validated, it opens the lock. If that is not done, it again checks whether the user has entered the password through the app. If it has been added, it opens the lock. If not, it starts going through the same process again and again. Once that is done and the lock is opened, the booking is marked as ended, and the robot can now move to the next booking.
This is the overarching physical architecture of the system, which was divided into different subsystems based on the interfacing requirements of the hardware and software. At the far right, we have the low-level sensors including the rotary encoder, which takes rotation data from the wheels and sends them up to the low-level controller, the Arduino, which then transmits this feedback data back to the high-level controller, the Raspberry Pi, and in turn receives actuation commands to move the wheels as required, forming a sort of closed loop. At the center is the Raspberry Pi block, the main controller on which all the ROS programs and algorithms are hosted, including path planning and obstacle avoidance. The Pi is communicating with the low-level interface on one side, the LiDAR, the camera, as well as the server-based backend on the other side. The server is coordinating with the app-based front-end for booking-related data management and also the facial recognition server for implementing the security features. Over to Saran for the next slide.
Our first prototype on your left was composed of three wheels, one caster and two driving. Through our experience with testing and via literature review, it was identified that the center of the gravity in such a robot design has to lay inside the triangle formed by the wheels. If too heavy of a mass is mounted onto one side of a free rotating wheel, the robot tips over. All of our major algorithm tests, localization and mapping, PID locomotion optimization, autonomous navigation, and obstacle detection and avoidance are performed on this prototype. However, due to the fact that this design was not suitable for the integration of the payload delivery system with the facial recognition and lock mechanisms, the group decided that it was best to come up with a new design and integrate all of the prior work in it during the final stages of the Kaavish project. Using Google SketchUp Pro software, the final robot prototype design proposed in Capstone 1 and Kaavish 1 is shown in the figure in the center. Due to the complexity of the proposed design and the unavailability of the 3D printing facility, this design was abandoned. The reimagined final prototype on the right is more stable than the three-wheel version because the center of gravity is to remain inside the quadrilateral formed by the four wheels instead of a triangle. Such a design allows the front wheels to give negligible resistance to the overall circular motion generated by the rear wheels when the robot takes a zero-radius 360-degree turn. Therefore, the torque applied by motors on each wheel gets harnessed properly and results in a better performance without any drag or wheel slip while taking a turn. In this slide, as you can see, these are our Corel Draw frame dimension documents for the bottom and top frames of our robot respectively. These were used for the laser cutting procedure on sheets of acrylic.
The video on the right shows the difference in the movement of the first prototype and the final prototype. As you can see, during the navigation, the final prototype movement is much smoother and faster than the first one. This is because of sharing computation of the navigation stack between our personal computer and the Pi, as the Pi cannot handle the amount of computation required by the navigation stack. The first point of operation of the robot is the manually implemented mapping process. Using a program node, the administrator can use his keyboard or other input medium to navigate the robot in a 2D floor plan to generate a map. A map is obtained which is loaded by the robot's navigator to situate itself. The visualization tool is used to observe the image. The thicker edges indicated the ends of the map and any fixed obstacles while mapping. The lighter gray area is the accessible area by the robot. Since obstacle detection and avoidance is a feature of the robot, for Kaavish 2 we decided to do some simulations to better understand the range and accuracy of the LiDAR. Using a simulation environment called Gazebo, we are able to capture how the LiDAR behaves with obstacles in its surroundings. And the real-time result of the simulation is visible in the screen to the right, showing the point clouds where the obstacle's edges are detected. The obstacle detection of the robot can be visualized using the RViz visualization tool. As you can see, the robot back shows the walls that is shaded by the black region over here. Now, as the robot moves, it detects an object ahead of it and tries to navigate across it. Unfortunately, the obstacle detection feature isn't perfect. However, that can be fixed by tuning the parameters more professionally, something we could have done if we were integrating the robot in the lab, but we couldn't due to the pandemic. As you can see, it's trying very hard to navigate across. This blob over here on the screen that is shaded in the black region is actually the obstacle. This is the visualization tool to help set the pose and plan a path. Using this tool, we extracted XY coordinates to situate as well as guide the robot. We had no live way to update the coordinates though, and that's something we could look at in the future.
Okay, so let's talk about the stack that we have used for our Android application. So our application is mainly built on Ionic, which uses Angular and Cordova plugins. So Cordova is basically an interface for accessing native features of the Android app, like touchscreen, camera, browser, etc. So the app is built on Ionic. Then we have the PHP server, which is on which our central server is created. So we have that server side, and then we have for database we have MySQL database.
To make facial recognition easier to implement on the hardware given, we built a server along with Python APIs. The robot listens for post requests from mobile at the event sign-up. It also listens for post request at the time of a completed delivery from the robot. Sending the inputs to the server CPUs, the trainer and the recognizer modules process inputs and output is sent via Flask GET APIs. Let us proceed to a visual demo of the robot's journey.
Now we'll be taking a quick look at the overview of the physical structure of the robot. Right at the front, we have the electromechanical payload box. As you can see, this is the compartment which houses the payload for delivery, and this is the solenoid lock that actually acts as the security implementation to secure the item within the box. At the bottom layer, we have housed all the power systems as well as the electronic components needed to run the robot. At the top is the LiDAR mounted for 2D environmental mapping. This is simply the connection between the LiDAR and the Raspberry Pi. This is the switch that activates the entire system. And finally, on the top, we have the Raspberry Pi camera, which serves as the medium for the facial recognition based security feature. Here you can see the backbone of this project, which is the LiDAR or light detection and ranging sensor, which is the 2D perception system used in this project. It operates at a 10 Hz scan speed, emits pulses of light, and receives the reflections and hence builds up the map around it using a process called scan matching.
So as we can see, this is the map making on our first prototype, which we presented in the Kaavish one. The process can be seen in the RViz, and the LiDAR is seeing functioning, and currently the robot, the first prototype, was stationary while doing this. This is the map mapping on the final prototype, which we have currently completed in the Kaavish 2. So this can be seen that the robot is currently being operated through telemetry from the laptop, and it is currently making the map of the room, which is uh, can be seen in the video. This is the map that was generated by the final prototype of our robot. As you can see, the boundaries of the room are visible. The gray area is inaccessible to the robot, and while the robot can move freely in the white region without any hindrance.
So this video it illustrates the sign up process. So the user first downloads the app from the Play Store, then starts by creating an account by specifying the name, email, and password. Once these details are added to the app, The user is then redirected to a page where he can add the face video. The user then uploads a 10 to 20 seconds video of his face from different angles to the central server so that the facial recognition server can train on that video so that that can be used to verify the receiver when a delivery is received. So a sample video can be shown on the screen now. So as you can see, Samir, our group partner, is recording a video from different angles, and then he will upload that video to the central server. Okay, so let's talk about the next process. So in this video, you can see the whole cycle of the person creating an account on the app. Then the person uploads the video of his face, a 20 seconds, a 20 to 10 seconds video of his face through the browser to the app. As you can see here, Hamza Azim, our group partner, is uploading his face video, and the face video is automatically uploaded to the server and appears here. So you can see here that the video got uploaded here successfully. Once that is done, the user can then start to initiate a booking. How this is done is you add your address. So we have added the right address. Then we add a receiver to which we want to send a parcel to. So he adds Samir Anis, and then we start the booking. So the live booking now they get shown onto the dashboard here. See, this live booking got shown here. So here you can see that how the person, when the robot reaches the person, the sender, it automatically opens the lock, and the sender then can place the parcel inside the compartment of the robot, and then can close it so the robot can then go to the receiver.
The following video shows the autonomous navigation behavior. It is the end-to-end video of the whole process. So firstly, the robot is in its initial position, and when we give the sender's position to the robot, it navigates itself over there. So it's now trying to navigate itself, moving smoothly, trying to navigate around its surroundings, and moving to the sender's location. I'll forward the video. Sorry for the video quality. The camera went out of focus. We tried numerous times to fix it, but we couldn't. This was the best possible result. We tried many videos, but this was the best result. Now it has arrived to its pickup location, and as you will see, the lock has opened for depositing the delivery item. Now it will take the receiver's goal and move over there. Sorry for the robot moving out of the frame. I'll forward the video. So now what it's doing is that what I'm doing is that I'm going to the app, going to the delivery details, and then trying to unlock the container using the password. I've now moved the camera to better oriented position. Now I'm going to enter the password and the lock will open. There we go, the lock opens for receiving the pin code. Next. So over here we will show the facial recognition part. So previously we showed the password way to unlock the box, but now we'll use the facial recognition way to unlock the box. I'll fast forward the video as it's the same thing. It's the same process. So over here what I'm doing is that I'm moving my face again and again so that the camera could recognize me. But the problem was the limitations of the lighting conditions. The lighting conditions were too bright, so it couldn't actually detect my face. Now when I turn off the light on this side, the robot will actually detect my face and it will open the lock. As you can see, the robot sends the image of my face to the server. The server recognizes that I'm Samir Jaliwala over here, and then it allows the lock to open. Moving on. So this is the failed attempt of the facial recognition. We'll show again the same process, the end-to-end result. I'll move to the end where it actually shows that it couldn't open the lock. Now it had recognized my face. I mean, it had detected my face, but it couldn't recognize it, who I was. So it sends this image to the server, and it sent a response of unknown. So it couldn't open, and then I had to open it using the password. And at the end, we would like to show the box unlock feature. So the box unlocks, I'll take out the parcel and then I'll close back the lock.
So after watching the video, the conclusion and the way forward for our team is we want to use the cameras and other kinds of sensors for sensor fusion for a better perception of movement and environment. Use of simulation to enhance the design and testing process with real world scenarios so that we can better the movement and optimize it further. Also, we want to use powerful batteries and motors to increase the life and mileage of our robot in view of other commercially available products. Thank you for watching our presentation, and we will be taking questions. Thank you.